So today's lesson is about magnetic force. And we start off by looking at things that we already know about, and then we build on that. So let's say we have two bar magnets right next to each other. Let's say this is the north, this is the south. And let's say this is the south, this is the north. And let's say they're on a real slippery table, and you put these two bar magnets down next to each other like that. Well, if they're strong enough bar magnets, what will they immediately do? Clink! They immediately slide right together. So they will immediately attract. And if you take a closer look at the invisible magnetic fields around the two bar magnets, you'll see that the field in between them is going in opposite directions. So if I draw the magnetic field around this bar magnet, it goes out of the north into the south like this. Out of the north into the south like this. And then this bar magnet goes out of the north into the south like this. Out of the north into the south like this. And if I take a close look at this area in between the two bar magnets right there, do you see how the field lines are going in the opposite direction? So when the field lines are in the opposite direction, they somehow attract each other. And not only do these field lines attract each other, they drag their objects inward as well. So field lines going in the opposite direction are attracted towards each other. And guess what's going to happen next time when we put the bar magnets so that the light poles are like right next to each other? They're going to repel. So if I have a bar magnet like this and another bar magnet like this, and let's say the two north poles are right next to each other and the two south poles are right next to each other, well, if I draw the magnetic fields around these guys, they're going to be going in the same direction, exactly. So, usually one of the bar magnets will like flip until the south pole will be attracted to the north. But if things were perfectly lined up, you just get a sheer repulsion force. You could bring this magnet here in closer, and if you just kind of push it closer, this one here would slide away. They would be repelling. It's kind of fun because you could push one magnet around and get it to move away without even touching it. So these two will repel because light poles repel. And again, if we take a close look at the magnetic field in the space in between, here the field lines are both going down. They're both going the same way. So, when field lines go the same way, they seem to push each other apart And not only do they push each other apart, they push their objects apart as well. So now we're going to look at things that we normally don't look at. I mean, this is stuff we've seen before. Oh, bar magnets, they repel and attract. Well, recently we learned that not only do bar magnets have magnetic fields around them, so do wires with electricity. More officially you could say current-carrying conductors. So let's say you have a wire with the current going up, and over here you have a wire with the current going down. Each of those wires has a magnetic field around it. And those magnetic fields are going to interact with each other, and basically there's going to be a magnetic force. Now, at first glance, you might be like, oh, look, the currents are opposite, and you might think back to, here where the poles were opposite, and think there's going to be an attraction. But it's a little bit more complicated, because you don't necessarily have to look at the currents. What you have to do is look at their magnetic fields. So let's say I grab this wire right here with my right hand. If I grab it right there, then on the right side, my thumb pointing up, my right hand, my fingers are going to be doing what on the right side of that wire? Going into the page. So the field right there is going into the page, and then if my right hand finger is curled all the way around the back of the wire, what would they be doing here on the left side, Paul? They'd be coming out of the page. Okay. Now, the magnetic field really looks like a circle. This is just a shortcut way of drawing it. If you wanted to draw it like a circle, you could draw it like this, like, and basically you would be coming around like this, and it goes, in over here, and comes out over there. And then what about the wire on the right? If I grab this wire over here with my right hand, this time my thumb will have to be pointing down. My fingers curl in the direction of the invisible magnetic field around the wire. So on the left side of the wire, what's the field going to be doing right there, Swati? Going in. And then over here on the right side, Swati?
Out.
Going out. Over here, current's going up. The current's going up. I have to put my thumb up. If I put my thumb up, see how it's going in right there? And then coming out. And again, it really looks like a circle. Going like that. So, this of course is occurring all through the wire. So even like up here, it's going in and coming out. Here it's going in and here it's coming out. So if we take a close look at the space in between the wire, reminds me of that Dave Matthews song. The space between where we are. Anyone know? Dave Matthews. Space between. Great song. iTunes or whatever you modern kids do. So basically, in the space between here, what are the invisible magnetic field lines doing? Are they going in the opposite direction or in the same direction? The same direction. Look, this wire here is going in. This wire over here, the field's going in. They're going the same way. And what do field lines do when they're going the same way? They repel each other. They push each other apart. So even though the currents are going in the opposite direction, the field lines right in here are going the same way, and those field lines are going to be pushing each other apart. Therefore, these wires are going to repel. And if the two wires had currents going in the same direction, current going up, current going up. Grab the left wire with your right hand. Thumb pointing in the direction of the current. Fingers curl around the wire on the right side of the left wire. Magnetic field line goes in, comes out on the other side. Same thing if I grab the right wire. Thumb going up because the current's going up. My right hand, the fingers go in on this side, would curl around and come out on the other side. I take a close look at the field lines in between the two wires. What's the orientation, Mr. Sandberg? Right there. Opposite, yes? So what are those wires going to be doing? They're going to attract. Who knew that magnetic forces could make wires repel and attract, just like bar magnets? So here, so we looked at the magnetic force between two bar magnets. And then we looked at the magnetic force between two current-carrying conductors. What if we looked at the magnetic force between a current-carrying conductor and a bar magnet? Ooh! That's just crazy talk. Instead of using just one bar magnet, we're going to use two anchored down bar magnets and a wire in between them. What I'm going to do is draw a three-dimensional drawing up top, this is the best I can, and then I'll give you the two-dimensional version down below. Sometimes people find that easier to interpret. So if you want to draw something three-dimensional, horizontal is like left and right, vertical is up and down, and then to give it depth, if you go at a 45-degree angle, it kind of makes it look like you're going inward somehow. So you draw that 45, comes over. So this is the north, this is the south, this is the south, this is the north. And let's say that these two bar magnets, of course, if they were free to move, they would attract. But let's say they're anchored down. Anchored down bar magnets. Now, I'm going to draw some lines here in between the two bar magnets, but then I'm going to erase them to make some room. So you might just want to hold off drawing in here. But the bottom line is, if you put a tiny imaginary compass right here, the little compass needle would swivel and stop like this, and basically, which pole would be over here? Claire? That would be the north. And Claire, over here? That would be the south. And whichever way the north pole of the compass points, that's the way the compass is said to be pointing. So it's like pointing that way. So basically, if the compass is pointing that way, we know the invisible magnetic field is going that way. So I know in between these two poles, the magnetic field lines are going north to south. Again, I'm going to erase some of these in a moment. So keep that in the back of your mind, how there's an invisible magnetic field. It's called the external magnetic field due to the bar magnets. So let me just get rid of some of this stuff here. Okay, and I think I'm just going to draw one over here, and I'm going to draw one over here. And then what I'm going to attempt to draw is a wire placed right in this way. Imagine if I had like a something, and I actually just push this right into the board, right in there. I'm putting a wire with electricity, just like this meter stick, and the charge is going to go into the board like this. So again, I try to make it look three-dimensional. Come back over here. So it's like the current is going into the page. If you want to just stick with this diagram, feel free just to stick with it. If you're having trouble, you could draw this next diagram, which is a two-dimensional. Oops. So let me draw the two-dimensional anchor down bar magnet, anchor down bar magnet, magnetic field lines going north to south, and then that wire with the current going into the page, I just draw as a circle with an X. Okay, and then I'll just make a little note that this thing right there, that's a wire with current into page. And that wire is the same as this wire up over here. Well, not only do the bar magnets have a magnetic field, but that wire has a magnetic field too. And Cedar, what does the magnetic field around a current carrying wire look like?
It's a circle.
It's a circle. So I'm going to draw that circle here. And I draw it like solid over here as if it's in front of the wire, and then I don't draw it over here as if it went behind the wire. Again, giving that three-dimensional look. And then I got to figure out which way it's going. So I grab the wire with my right hand. I grab the wire with the right hand. Thumb going in the direction of the current. My fingers curl around. So what's the magnetic field above the wire? Which way is it going to be going right there, Jacob? Left or right? Careful. Right hand. Fingers. It's like, like this is the wire. Fingers going that way on top and that way underneath. I know, it's tricky to see. And then underneath, they're going down like that. And if I draw the magnetic field around this wire, again, it looks like a circle. And would it be going clockwise or counterclockwise? Read?
It would be going so clockwise.
Clockwise. Okay, now we get into the nitty-gritty. Check out this space right here. Check out this space right here. That space right there, people. How is the bar magnet's magnetic field, the red line, and the current carrying conductor's magnetic field, the orange line, how are they orientated relative to each other? They're going in the same direction. So guess what those field lines are going to do? They're going to repel. And when they repel, whoa, that's going to push that orange field line down. And not only does it push the orange field line down, but it also pushes the wire down. Yes? And then let's look at the space underneath the wire. Like right over, right underneath here. Notice the bar magnet's magnetic field, the red line, that's going to the right, but the current carrying conductor's magnetic field is going to the left. So they're going in the opposite direction, and what do field lines in the opposite direction do? They attract, so that's going to attract that orange one down, and not only does it attract the orange line down, but it also pulls down the wire as well. So both the repelling force on top and the attracting force underneath ultimately makes the wire move which way? Down. So the wire experiences a force down. Whoopsie. Same thing with that bottom diagram. Look, right here. Whoopsie. Right here in this space right here. Notice the field lines are going the same way, so they're going to repel each other. And then underneath here, these field lines are going the opposite way, so they're going to attract each other, and the repulsion force on top and the attraction force underneath ends up pushing the wire, down to the ground. Oh. The good news is, Polly, you don't have to go through and look at the little baby red lines and the orange lines and look to see, oh, look, they're going the same way. That's going to repel. Oh, look underneath. They're going the opposite way. That's going to attract. There's a third right-hand rule that'll tell you the direction of the magnetic force on a current-carrying wire. You all ready for this?
Is there a right-hand rule that's solving 100?
Yes. You take the food in your right hand and you offer it.
It's right in front of the
No, that's a good point. All right, ladies and gentlemen, here's how it goes. Basically, you take your fingers and your thumb and you keep your hand flat this time. No curling around a wire, no looking at your fingernails two different ways. You just keep that hand flat. Fingers and thumb. And your fingers and your thumb of your right hand should be at a right angle to each other. Okay? Then you take your fingers and you put your fingers in the direction of the magnetic field lines due to the bar magnet. That's called the external magnetic field lines. Not the field line of the wire, but the field lines due to the bar magnet. Here in my diagrams, the red lines. So the red lines are going to the right. Yes? Keeping the fingers going with the red lines turn your hand so that your thumb is in the direction of the current in the wire. See, if I start to turn this way, whoops, wrong way. Gotta go back to, oh, now, see how my thumb's going into the page? Just like the current is going into the page, yes? My fingers are going with those red lines. My thumb is going with the current in the wire. The force, I didn't make these up, guys. The force magically comes out of the palm of your hand. Mwah! Mwah! The force just comes out of the palm of your hand. Mwah! So if you were going to attempt to draw this thing, it would, it would look something like this. Fingers. Thumb. Your fingers go with the external magnetic field. That's the magnetic field of the bar magnet. Your thumb goes with the current, and the force magically comes out of the palm of your hand. So let me write that down. If you don't feel this is necessary to write all this out, feel free not to. Used to determine the direction of the magnetic force on a wire with electricity in it, a current carrying conductor, that's in a magnetic field. So basically, keep, and I'm just going to finish writing this out, but feel free to take a break and come on back. Okay.
I actually never got the right two.
Okay, I can get them for you.
Now that it's due Monday, I can give it to you tomorrow.
This one working
Okay, keep your hand flat.
And like they got
yeah, it's only one day. Oh, you have AC. Hey, you're in theory.
yeah. I like to go to that part of it. So yeah, when did that come to?
Water there.
So yeah.
Oh my God, she's there. Yeah, but she was there last time.
It's like fishing in a can.
She's all there. Rachel?
One second.